did last time. But first I have to correct a formula that was not given correctly in the manuscript and led to some discussion. So in the formula that relates the slip velocity to the stress ratio, what I had F there, but it should be the inverse of F, or better expressed, I would say, the slip velocity normalized by the square root of the velocity fluctuation, or the strength of the velocity fluctuations, is F times the stress ratio. So in answer to Professor Chatterjee's question about what's happening when this is becoming singular, what's happening when the bumpiness goes to zero, well, as F becomes singular, as the boundaries become smooth, the slip velocity goes to infinity. So that's the explanation. I'm sorry. I'm sorry for having made that mistake originally, but not having seen it as we discussed it last time. Okay, so that hangs together, and the correct version of it was used in the calculation of the profiles. Okay, so what did we get last time? We saw that the implementation of this rather crude theory for shearing flows, or flows in general, of dense, nearly elastic spherical particles led to equations of balance and associated constitutive relations and boundary conditions that we could employ to phrase a boundary value problem, at least for steady, fully developed flow. So only one spatial dimension is varying, and that the fields are varying with that spatial dimension normal to the flow. And we provided profiles here, and I've reproduced them in a way that's too small for you to read the issues or the versions of the parameters. But I should say here I'm showing profiles at a single angle of inclination for various values of the velocity at the top. So these are velocity profiles, and the velocity profiles are increasing, or the magnitude of the velocity at the top is increasing, and consequently the entire profile is increasing. And each then has a slip, a predicted slip at the bed. That is, this value of slip velocity at the bed is part of the solution. And also there are predicted profiles of the granular temperature, the strength of the velocity fluctuations. And here it's not t that I'm plotting, but the square root of t, which is what the linear equation governed. Okay, so we're predicting profiles that appear to be perfectly good. Similarly, we can get profiles of the volume fraction in this region. They seem to vary between 0.4 and 0.6, and these particular profiles are profiles that are given for values of the coefficients of restitution of flow, and flow wall collisions of 0.9. A given bumpiness is slightly more bumpy than hexagonal close pack of identical spheres, and I think a given value of u for various angles of inclination. And what we see is, well, what we saw earlier, let's say, is a single flow depth. So where have I? So here I do. Yeah. Okay. What we saw earlier is that the flow depth is a unique function of the angle of inclination. So given an angle of inclination, there's only one flow depth, and if we want to push more material down that angle of inclination, then the velocity profile has to increase, or the volume fraction has to increase. So that was one thing that we determined, and the other is that the volume fraction here increases with the angle of inclination. So we have to keep those two features in mind because we're going to test them next. we're going to test them next by comparing what these predictions are with the results of numerical simulations of incline flows. Okay, this just repeats what I've said. And there are several simulations that have been carried out on incline flows. This is perhaps the most complete one. So this is a slice from a numerical simulation of flow over a bumpy, rigid inclined base. You see that it's rather deep in terms of numbers of particles, perhaps on the order of 40 particle diameters here. And it's a steady simulation in which the forward and the backward, that this cell is periodically repeated up and down the incline, and it's also periodically repeated away in the direction perpendicular to the board. Okay, so the surface here is free, and gravity then drives a flow that really particles will essentially flow out the forward part of the cell and reappear at the backward part of the cell in the steady state. And the particles are interacting through a collision law that involves a normal coefficient of restitution, and in this instance, a tangential restitution coefficient and sliding friction. Okay, so I should say something about how we make the connection between a theory that is ostensibly for frictionless spheres and a simulation that certainly involves friction. So what we do is if we were to do something, if we do it in great detail, we would have to introduce additional balance equations for the angular momentum of the system. That is, each grain is going to have a rotational velocity, and certainly the rotational velocities of different grains is going to differ, but there's going to be an average rotational velocity, and there are going to be fluctuations at any point in the flow from that average velocity fluctuation. Okay, so to do the problem correctly and completely, we're going to have to introduce a balance equation for the average angular velocity, and that's the angular momentum balance. And we're going to have to introduce a balance equation for the strength of the rotational velocity fluctuations. There's energy, significant energy, associated with those. So we're going to have to deal with 4 additional balance equations and boundary conditions that are associated with each of those equations. So that's something we don't want to do. So we take a cruder approach. So we find, if you looked at that more complicated theory, you would find that the rate of collisional dissipation, depends not only on the normal coefficient of restitution, but also the tangential coefficient of restitution, and the coefficient of sliding friction, and effectively the strength of the rotational fluctuations. Now, I'll put both of these here. This measure the strength of the translational velocity fluctuations, and a measure of the strength of the rotational velocity fluctuation. Okay, so what is mu? Mu is the coefficient of sliding friction here. Maybe I should. Have I used mu in a different way before? So this is the let's say, I'll say rotational temperature. Okay, it's a measure of the kinetic energy of the deviations of the rotations from their average value. Okay, so we've got this, and then we have an angular momentum equation. And the angular momentum equation, let's say, gives us the average of the particle rotation. Okay, and the energy and the rotational energy equation deals with the determination of the rotational temperature. Okay, so what we do is we phrase and solve, and it's relatively easy to do. We solve these in simple shear.
The energy equation is still only one of them, right?
Yeah, it's a scalar. It's a scalar measure.
Theta will be there with T also.
That is, the equations are typically coupled. Yeah, what do you mean? We'll have an equation for T and we'll have an equation for theta.
That's good, because I thought that the energy equation would be only one. You can't separate out the. How will you separate out the translational part from the rotational?
Well, the translational part only has to do with the kinetic energy of the centers of the particles.
No, in terms of balance, the energy balance will be only one. It will include both translation and rotational.
Well, you can write a balance equation for both. I mean, neither is conserved, and you can write balance equations for both, and they're coupled.
They're coupled. Okay.
Yeah. Okay. So I'm going to say. So what we do is we solve these in simple shear. And when you solve those in simple shear, what results is that the average of the particle rotation is 1/2 the vorticity of the mean velocity. Okay, so that the rotations of the particles, average rotation of the particles, related to the average rotation of the flow. That's fine. Okay, so that's nothing to do with that. And what you're able to do is and now from the rotational energy balance, you're able to express theta, the rotational energy, in terms of E, ET, mu, and T in this simple situation. So you substitute that in here. You substitute that in here, and that enables you to define an effective coefficient of restitution. Of normal restitution. Okay, and that effective coefficient of normal restitution is expressed in terms of the real coefficient of normal restitution, coefficient of tangential restitution, coefficient of sliding friction, and the translational temperature. So what we're doing then is we're taking the influence of the rotational degrees of freedom and the energetics associated with those rotational degrees of freedom into account in the translational energy equation only. So that's the only place that friction is playing a role. We're not taking it into account, let's say, explicitly in the shear stress or the pressure. The only way the frictional aspects of the interaction appear in those is through the modification of the temperature associated with the additional mechanism of dissipation. And there are two additional mechanisms of dissipation, if you like. There is the dissipation associated with the sliding friction itself, and there's an effective dissipation associated with the total fluctuation energy of the system is separated into translational fluctuations and rotational fluctuations. So we've got some energy that's in rotational fluctuations that we wouldn't have if we had a purely frictionless system, but this way of solving the rotational energy equation incorporates those too. That is, the determination of theta in terms of T accounts for both frictional dissipation and the fact that we have rotational and translational temperature.
The determination of theta is analytical or numerical, or how do
You can determine it analytically in the limit of small sliding friction and in the limit of large sliding friction, and otherwise you have to do it numerically. But the point is, given the appropriate inputs, there's a simple M file in MATLAB that gives you the number then for the effective coefficient of restitution. Okay?
And the other one is omega is half V cross 10 to the
No, omega z cross u. This is the average flow velocity. So the average of the particle rotations in a simple steady shearing flow is half the vorticity of the mean flow.
independent of the diameter.
Yes. Okay. So that's the way I'm going to try to connect the theory for the frictionless particles, spheres, that we have been talking about up to this point, and the results of numerical simulations on frictional spheres. I'm going to make use of this effective coefficient of restitution.
So is that easy to see? Omega is equal to half V cross.
Pardon me? Is what?
Curl of U. Yes, half the vorticity.
Yeah, half the vorticity is the average, is the angular velocity of the flow. Okay, so the angular velocity of flow is the same as the average angular velocity of the particles in steady simple shearing. That's all. I mean, that's not a surprise, really.
I was confusing it with particle rotation, but it is not what you are.
Yeah, but of course, in these flows, that's not the case. That's only an approximation.
Yeah, so you are assuming that the particle rotation is same as the global rotation.
Of the flow rotation, exactly. Yeah, but I mean, that comes out as a result of looking at the angular momentum balance if you've derived it. Yeah. Okay. So what else can I say about this flow? Okay, well, this is the simulation cell that Silbert and his colleagues made use of, and let's look at their results. So here are their results. This is the angle of inclination. Here, this is the depth of the flow from bottom to top. Here the cell's about 40 inch diameters. And let's see. And what we see from here is that I'm sorry. Did I say angle of inclination? No. Theta is the angle of inclination. Phi is what I call nu, the volume fraction. Okay, see, the problem with the subject is that each discipline introduces the notation that's more familiar to them. And typically, chemical engineers will indicate volume fraction by phi. Civil engineers will deal in terms of the concentration, and those involved in kinetic theory will use nu. So there's plenty of reasons for confusion. But the point is here, that this is the volume fraction. The Silbert simulations show that the density profile, or the volume fraction profile, is pretty much uniform, at least for angles of inclination, let's say between 20 and I think this is, 24. Okay? So that differs from the predictions that we saw earlier. That is, we had certainly some curvature to the profiles, but the more important difference is what Silbert simulations show is that the simulations that are at the smallest angle of inclinations are the densest. And remember, what we predicted was that the predictions were that the the flows at the highest angles of inclination were the densest. So we have a reversal, complete reversal between the predictions that we talked about earlier and what's observed in this simulation. Okay?
Simulation is constrained because it is periodic in both directions. So in that sort of inclined rectangular volume, particles cannot enter or leave. Anything that comes out on this side is re-injected from that side.
That's true.
So
But that's a characteristic of let's say, of a fully developed flow, a uniform flow.
no, but the uniform developed flow may not have that many particles.
May not have that many particles.
Yeah, the
Yeah.
particles could spread out, and then if you had an actual flow, you would not be able to say in advance how many particles there are in any projected rectangular area.
Yes, but say given a number of particles in the cell, you can imagine a real flow that had exactly the same number of particles. I mean, I believe in the veracity of this simulation.
No, the simulation result
Yeah.
is done by competent people under some
Yeah.
assumptions. There is no doubt about.
But then I don't understand what you're saying.
See, one might also imagine that in a steady flow down a chute, it is possible by injecting different amounts of particles to achieve different heights for the same slope. But your theory shows otherwise. So it was surprising.
Yeah, well, the theory shows otherwise. I haven't exhausted the simulations yet. Okay.
So, but what I'm saying
Yeah.
is our prior intuitions may or may not be correct, and we have to sort of stay open-minded. So in the same way, I mean, suppose I had a very long chute,
Yeah.
and I sort of packed it up to some height, and then I let it go. So it's sort of going, and it's infinitely long, and it reaches some steady state. It might spread out along the chute. And
Yeah, so the height decreases until it reaches some
yes.
steady, fully developed height.
So the number of particles there may not be in my control. I may not be able to specify in advance the number of particles per unit footprint.
Okay, so you're saying that in this simulation, let's,
They have
I agree with everything you say.
They've arbitrarily assigned it and forced the simulation to hold it constant.
Okay, I understand, yeah. And that certainly would be at odds with the predictions that I showed the earlier theory. Okay, so we're going to see in the next slide that in fact we can have any depth at a given angle of inclination. Okay, so a second prediction of the simple theory is going to be obliterated. All right, so and that makes your objection perhaps to the simulation here maybe almost empty, because if you can have a flow at any depth at a given angle of inclination, then you can fill the cell however you like. Yeah, but I understand what you're saying. This simulation is not consistent with the result that we got earlier, because he might not, I mean, I would
An
say,
added constraint that we did not impose earlier.
yeah, but I would say in that instance, what they would see in this simulation is unsteadiness. The simulation would not be able to settle down to a steady solution because its depth was not the exact depth that was required if the earlier theory was true.
It has the degree of freedom of changing its volume
That-
fraction.
that's
It
what
does
I'm
have
saying.
that overall average degree of freedom. But in some sense, people are not allowed to leave the room.
You're right. No, they don't. You have the same number of particles through the entire simulation.
But in a long chute, that would not be the case.
Yes. Well, yes, according to the earlier theory. All right, so let me show you the next simulation. All right, so we understand what's happening here. Another simulation done by Matari and Nakanishi, and this is done on disks rather than spheres. Okay, but the qualitative predictions are going to be, and here, once again, it's a little bit hard to see, but here, for example, they do two simulations at the same angle, 20 degrees. One simulation has this depth, and the other simulation has this depth. And they can get steady, fully developed solutions at any depth between those two. Okay? So that's one lesson to be learned from these simulations. And what else? Well, once again, over the bulk of the flow, the volume fraction is uniform, and also the volume fraction is greatest for the angle, the smallest angle of inclination. So this is a volume fraction of, for 20-degree angle of inclination, this is the volume fraction for 23-degree inclination. And here, so what do they use for volume? Yeah, they use nu, okay. And because they're dealing with disks, their volume fraction, the random close packing of circular disks is an area fraction of 82%. Okay, so they're approaching the largest volume fraction that you can imagine. Okay, and they show temperature profiles. We'll just say that the temperature is not monotone. There's a region near the base that is strongly influenced by the nature of the base. Again, they use bumpy. They glue in their simulation disks of a slightly larger diameter than their flow particles to the bed. So they create a bumpy boundary, and that boundary does influence what's happening in the neighborhood of the bed. But in this core region, and we're going to be focusing pretty much on that core region, in that core region they find that the temperature decreases as you move towards the free surface. Okay, and one other thing that they found that was rather interesting is that they calculated the divergence of the energy flux across the flow. And that's a term in the energy balance. And they found that the divergence of the energy flux is essentially zero across the flow. So that the divergence term in the energy balance doesn't appear to be playing any role. It seems as if the energy balance is an algebraic balance between the rate at which fluctuation energy is put in through collisions driven by the average velocity and the rate at which is taken out by the fact that the collisions are dissipated. Okay, yeah, so those are the takeaways. Those are the takeaways from these simulations. Okay. So the earlier theory is seriously challenged, if you like. And let's try to get an understanding of why that might be. So here are numerical simulations done on disks, and in contrast to these simulations are done with rigid circular disks. These simulations are done with somewhat slightly compliant circular disks. There are two ways to carry out these simulations. If you have hard spheres or disks, then you simply, so you put in some kind of a detection routine that tells you when a collision is going to take place, and when that collision takes place, you simply you relate the velocities, the translational and rotational velocities after the collisions through the translational and rotational velocities before the collisions through the collision parameters. Okay? Now that's one kind of a simulation. The other is that you have soft particles that can interpenetrate slightly, and then you model the resistance to that interpenetration, both normal and tangential. And then each collision has a finite duration, and you're computing through the duration of that collision. Okay, so the hard particle simulations take a long time to run when you're in a dense situation. So people who typically doing dense flows make use of soft particle simulations because they run not only faster, but they don't break down. There are ways that a hard particle simulation breaks down. Okay, so these guys are using slightly or soft particles, and they're shearing. That is, the top boundary is moving relative to the bottom boundary, and the two images here have to do with exactly the same disks and exactly the same shear rate, but what has changed is the coefficient of restitution. So these might be frictionless disks. I forget exactly. And what they see and what they're plotting here, what the colored features are that they're plotting are overlapping disks. Okay, so they take a snapshot of the simulation at some time, and they color the disks that are in overlapping context. So what we see here, let's say at a coefficient of restitution of 0.92, there's not too many overlaps, and it looks like the overlaps are pretty much limited to at most several particles. It doesn't seem to be any orientation, perhaps, of these little chains of overlapping particles. Okay, but when you get a coefficient of restitution of 0, and that just simply means that the normal velocity of the normal component of relative velocity of the two particles is killed out entirely in a collision, but of course they're still moving tangentially, so the particles aren't necessarily sticking together. When they do that, what they see is the formulation of larger clusters, and these clusters have a preferential orientation along the axis of greatest compression in the flow. So if this is a shear, you've got an eigenvalue at 45 degrees here of the rate of deformation tensor, and you got an eigenvalue here at 40, well, this is 135 degrees to the flow direction. This is 45 degrees. This is compression, and this is tension. Okay, so it seems as if clusters of a certain size are growing along the principal axis of greatest rate of compression. And this is clearly in violation of that assumption of molecular chaos. The assumption of molecular chaos says that the velocities are uncorrelated, the positions are uncorrelated, every collision between pairs of particles takes place in a binary fashion without any memory of where they were before the collision. So you throw that assumption out the window. So the indication is that's how the simple theory that we were talking about is failing. Is one of the primitive assumptions in that theory, where we took the complete pair distribution function for colliding particles to be the product of a function of volume fraction alone and the two single particle Maxwellians. No, it's just not working. Okay.
But that is perhaps because we are taking E at 0.
Yeah, well, you're right. I would say that's failing. That here, it's clearly failing because in situations where the dissipation is significant. Okay, that's true. On the other hand, in Silbert's simulation, the effective coefficient of restitution is something like maybe 0.47. So that's a very dissipative system. Okay, so if it's failing here, we can infer that it's likely to be failing in Silbert's system and also in Nakanishi, Matari and Nakanishi's. Yeah, you're absolutely right. But typical systems of our interest are dissipative. Okay, their exceptional systems are the nearly elastic systems.
The size of these objects will be set by EP, the tangential distribution.
Well, I'll say something about that. That is, I'll talk about how we might understand the size of the clusters. Okay, and also I should say that, well, so we have these clusters. I mean, a fair question might be, what happens if a cluster spans the entire cell? Okay, which is possible. And and if the cluster is spanning the entire cell, then it may be that in addition to collisions, there's another mechanism for transferring force across the cell, and that is it's being directly transmitted by the force in these clusters, because these clusters are contacting particles. Okay? So we might say that in that event, all bets are off, because it's not purely a collisional system anymore. It's collisional plus perhaps elastic. It's more viscoelastic than viscous. Okay?
And one more question in the previous slide.
Yeah. Previous?
So these simulations, how is f of function of theta coming into the picture? That is
How is what?
f of theta, which we have seen at the beginning of the lecture as a correction, s f inverse of s by rho at the
Oh,
base.
okay. Yeah. So that's what that's determining is the energy that's determining the slip velocity at the base. And it also influences the energy transfer at the base. So that particular function has to do with what's happening here, and in fact, they employed two different bases. So the red line is one base, and all the rest of them are the other bases. So that I guess this is, let's see. Yeah, so this must be a very energetic base, and this is a less energetic base. But that, in answer to your question, that's principally affecting the features of the flow in the neighborhood of the rigid bumpy base.
So when a particle collides, their relative orientation is not considered. But when a particle collides with the base, the theta, at every instant, during every collision, they'll draw the normal between, they'll draw a line connecting the centers of the particles and calculate theta.
What do?
Yeah.
They simply, so they have a contact rule for every collision. Collisions between particles in the flow, collisions between particles of the bed. So they treat particles of the bed pretty much in the same way they treat particles of the flow, except the particles in the bed aren't moving. So there's a slightly different collision law for that.
But what about theta? Because
Well, but they don't need theta, because in the simulation, the particles of the bed naturally shadow what's happening in the simulation. Theta was the way that the shadowing of neighbors for collisions entered the analytical theory, entered the formulas for the exchange of momentum and energy. But you're doing the simulation, you just let the particles individually collide with one another. And then you do averaging. So these profiles I'm showing you are due to averaging over strips in the simulation. Okay, is that clear? I mean, what's happening is they have a cloud of particles, and each particle is moving according to Newton's law of motion and taking into account the impact of collisions when the collisions occur. Okay, so here are more results from the simulation by Matari and Nakanishi. And what these, I should have said something about so there's something called T tilde here, which is the rotational temperature. It's what I called capital theta. And they show, and at different angles of inclination, the ratio of the rotational temperature to the translational temperature has different values. Okay, so that's something they calculate too. They calculate what I would say is the ratio of capital theta to T at various angles of inclination. So that information is available too, and they're showing it on their figures. Okay, so here are some more results. So they say let's take the kinetic theory predictions for the pressure. So we're going to take the pressure, they call it N for normal stress, divided by the temperature, and what results is a function only of area fraction in that case. And the kinetic theory, similar to what we derive for spheres, the kinetic theory for disks, makes a certain prediction. And they show that prediction is pretty good over a wide range of area fractions. So it doesn't seem like the deviations that they're seeing have anything to do with a failure of the kinetic theory with regard to the pressure, prediction of the pressure. And they do a similar thing for the shear stress. And once again, they find that the predictions of kinetic theory doing pretty well for various angles of inclination over the entire range of area fraction. But something they observe is that for the rate of collisional dissipation, the kinetic theory predictions seem more singular than what they observe in the simulations. So it looks like if there's a failure, let's say in the constitutive relations that we've derived, or that corresponds to the ones we've derived, it's in the rate of collisional dissipation. Okay, so let's just keep that in mind. Something else they show, or I should say, so these are all the curves of their simulation. They also show the result that would be obtained in this instance if the system obeyed equipartition of energy. So in a molecular system where you have elastic collisions, you expect that the rotational energy is equal to the translational energy at any point in the flow, any point in the system. Okay? So they show that simply to place in that context what they observed in their simulation. Okay, so finally, they look at an expression for the tangent of the angle of inclination versus the volume fraction. And although I didn't emphasize this when we talked about the simple theory, or its analog in 2 dimensions, of the theory we talked about would say that the tangent of the angle of inclination in this flow as a function of solid fraction is a series of straight lines. And if you use the more refined theory that comes from solving the Chapman-Enskog relations, those straight, the horizontal straight lines of the simple theory become slightly inclined straight lines. So this is a prediction of kinetic theory, and this is what they observe in their simulation. Okay, so a significant departure from that prediction of the kinetic theory for the tangent of inclination as a function of area fraction. Okay? So,
Area fraction where? Area fraction is what?
well, as the area fraction varies through the flow.
Yeah, so at which point?
Well, but this is at points, all points in the flow. I mean, you pick a point in the flow, you see what the area fraction is, and let's see. Well, so, okay, given an angle of inclination, you can the better way to solve it or to answer it is this: is that they're making these measurements in the portion of the flow in which the area fraction is uniform.
Okay. So basically they're averaging it through most of the bulk.
Yeah, exactly. I mean, it's not really an average because the area fraction is constant there. So they're not focusing their attention on what's happening near the bed or what's happening near the free surface. Okay.
Can I just
Yes,
seek
please.
clarification? So you start the simulation, you put a certain number of disks inside that rectangular area.
Yes.
You have a free parameter, which is the slope of the incline, and then you let it run, and presumably it reaches steady state.
Yes.
And when it does, it has this degree of freedom of spreading out more or less, and therefore the simulation gives you an area fraction, in a sense, at the end for the developed flow.
Well, let's say it gives you an average area fraction,
Yes.
if you like.
Yes.
In this instance, it turns out that the area fraction is uniform over,
Yes.
yeah.
So in some sense, in the simulation, you fix the inclination in advance, and the area fraction comes out of the simulation.
Yeah.
And then you have several simulations, then you have those points in the.
Yes, that's right. Okay, but that would be, suppose though the area fraction is varying strongly throughout the flow, then what you say applies to the depth averaged area fraction.
Yes.
Yes. Okay, but here it's okay. Anything else?
Because in the theory, the area fraction was exactly constant.
In what theory?
No, yeah.
No, it was.
No, it wasn't. No, we had significant variations across the flow.
Yeah, it was constant through most of the bulk except in the tops, bottom, right?
No, I would say that. So I would say the profile looked like this. Let's see. Something like that. Okay. I mean, you're saying, well, it's-
So in the theory, then the lines correspond to averaged.
here it would.
No, when you are comparing in the next figure,
No. It's this. They have essentially a constant.
no, when you are drawing lines in the next figure, in the subsequent slide, when you are comparing, the bottom right one, those lines,
Oh yeah, you're right. The lines are averages. Yeah, you're right. That's a good point. Yes, you're right. Okay. So what I'd like to do is I'd like to attempt to modify the kinetic theory that we talked about in as simple a way as possible in order to have the resulting theory reproduce these features. That's what I'm doing, okay? Now, I should say also that this situation we're in which the simple kinetic theory has failed, apparently, this is exactly the situation in which the mu I rheology that you've been introduced to earlier, this is where the mu I rheology is going to work, okay? That is, it's more or less indifferent as to what's happening in the microscopic level, but phenomenologically, it is able to predict in this regime. Okay, so that's where the mu I rheology fits in with the kinetic theory. It operates here, and in fact, it operates all the way to yield. Okay, and I would say the best we can hope for a kinetic theory is for the kinetic theory to work all the way until the clusters eventually span the cell. Then we're finished. Okay, but the mu I rheology, it works for those systems as well, apparently. Okay, so this is what we're going to do. Because it seemed as if the rate of collisional dissipation was the one constitutive variable that was influenced in the Matari-Nakanishi simulation, we're going to try to modify that. And the modification that we're going to introduce is we're going to introduce a length scale other than the particle diameter in the rate of collisional dissipation. Typically, this was the particle diameter. Now we're going to put a length scale in that we're going to determine somehow, and we're going to identify it with the size of a cluster. Okay? And also we see, by looking at the simulations more closely, that the volume fraction dependence becomes singular for frictional spheres at some other volume fraction than 0.64. It becomes singular before random close packing. Okay? And that might have to do with it becoming singular because frictional particles begin to span the cell earlier than frictionless particles. Something like that. Okay? So those two quantities are going to be modified. All right. So then the question is, how do we determine the cluster size? And we do this is phenomenological now. We're just making this up. Okay? But we have a story to tell, of course.
How do you get an L in the gamma equation?
Pardon me?
How do you get an L in the gamma equation?
Well, we've replaced a length scale, that is the particle diameter in that equation, with a length scale to be determined.
So the E would also not be particle E anymore.
No, we'll keep that. Yeah, we'll keep that.
I mean, potentially it will be lower.
Pardon me?
It's kind of fluffier, so it might be lower.
Well, I would say we have a mixture now of collisional flows, and I should say, in the Matari-Nakanishi calculation with hard particles, there's no overlap. What replaces the overlap are intense velocity correlations. So where Lois and his co-workers would see particle overlap in different colors, what Matari and Nakanishi see are numerous repeated collisions where the particles would be overlapping in the Lois simulation. Okay, so these chattering collisions, that's a complete breakdown of the assumption of velocities not being correlated. You have, okay, so that in a hard sphere sim, so in other words, that's a completely collisional theory. But we need the additional length scale is going to, in a sense, compensate for that. Okay.
So previously, instead of L, you had a D
Yes.
or sigma.
Yes. The particle diameter. So L is, as far as we're concerned, is going to be larger than a particle diameter. If it turns out that L, as determined by however we determine it, is equal to the particle diameter or less, we'll replace L with the particle diameter. Then we're back to the old theory. Okay? So how do we determine L? So here's the story, is that L is determined by a competition between the mean shearing, making clusters at 135 degrees to the flow, and the temperature attempting to randomize things. Okay, so that's the picture of how these clusters are developing. Okay, and then the phenomenology comes in by saying, well, how does this depend upon the volume fraction? And there's going to be some numerical coefficient in there. So we make let's say a guess. But of course we've got the simulation results at our disposal, so the guess that we make is going to be consistent with what we see in the simulations. So what we're going to say is it's going to depend upon G here to the power 1/3, and we'll put in a coefficient of order 1. Okay, so that's the way we're going to determine L. And of course L is being determined by fields of temperature and mean velocity that are determined in the usual way by the balance laws and constitutive relations. So we've made this one change, okay? And now let's see.
The du prime by T1.
This is the product of the diameter and the shear rate.
I'm sorry, I haven't listened to Herbert's stuff. Is that just dimensional analysis, or is that something?
Well, this is a parameter that appears again and again, this ratio in the kinetic theory.
L by D is dimensionless. I was wondering.
But I mean, it really didn't arise, let's say, by considerations of dimensional analysis, although you say it's dimensionless. But these are two different physical mechanisms that influence the interaction between particles. So, I mean, that's the average motion, forcing the particles together on average, and the fluctuations attempting to destroy any order in the system.
I was just wondering whether are there any other possibilities, or is that the only one we will have in a simple?
I think that's the only one that's possible. I mean, we're talking about a very simple flow here.
No,
So
in a simple sharing flow, there are not very many other variables.
No, none that I can think of. Combinations of variables. No.
Can I ask Isham's question in a different way? Why couldn't it be du prime squared over t?
It could be.
Oh, sorry, the example I gave, it is. Du prime squared over t to the half.
Well, I mean, so there you have problems with dimensions, right?
Well, that seems to be the point, isn't it? There's nothing else that could be brought in to make those dimensions balance.
Yes,
Yes, there is nothing else.
there is nothing
Well,
else.
then I think that's what Isham's question is related to. Saying
Yes, there's nothing else.
You could have, you know, the RMS value of the vertical component of the fluctuation in velocity. I mean, you can make things up.
You-
I don't
yeah.
think they're relevant.
Yeah, I mean, I guess you could, yeah.
So it's, among the variables you have, this seems like a likely candidate for, right? I mean,
Yeah, I mean, so maybe I have to admit that I was influenced by my background in liquid crystals. And there is the order in liquid crystals is related to a quantity like this, in a phenomenological theory. Okay,
Because I was struggling with relating those force clusters. I see you in avoiding force chains.
well, so in the jargon of the subject, the features that I call clusters are often called force chains. It's just that they resemble more clusters in this simulation. But in other instances, experiments, there are chains. So what's the difference between a cluster and a chain? I guess just the thickness of the ordering.
So I was struggling with when you look at that, it looks like a macroscopic input of energy, du prime, or not energy, I suppose. How should I think of du prime? Anyway, and there is a microscopic.
Well, du prime is the velocity.
du prime, yeah, it's the velocity, but times change in velocity.
velocity change per particle.
Per
diameter.
particle. Over the microscopic changes in velocity, which is t half. So, but the way you said it was, this is the competition between a mechanism which is forming force clusters and a mechanism which is trying to destroy it. And
Yes.
you could not relate the formula to physics. So I was trying to figure out how you would connect it. I mean, if I was to say that I would like to compare a mechanism which makes chains to a mechanism which destroys chains, immediately that is not what would jump out of the mind.
What would come to mind?
The shear rate is what leads to the compression at 45 degrees. So that's in the numerator.
Yeah, that seems clear to me.
And the fluctuations are
It-
what sort of breaks them up.
Yeah.
The chain collapses. And so that's in the denominator. You could flip it, and then physics wouldn't match or something. But right.
I agree, yeah. Okay, I mean, it seems clear that temperature is a randomizing influence. It wants to break up the chains by colliding. That is, where you don't have particles instantaneously in contact, you've got particles that are colliding against them. Okay, and also, maybe it's obvious, but these clusters are ephemeral, because the average shearing is constantly breaking them up. Okay.
In other words, is it true that if you have, when is L larger? Do simulations tend to indicate they are larger for U prime larger?
Yes, yeah. Yeah, you can do simulations and you can plot L versus U prime over T to the, du prime over T to the 1/2 and determine the relationship between them. Okay.
So the question, there is no tangential coefficient of restitution in this theory?
Yes, there is a tangential coefficient of restitution in the theory, but that's taken care of that is featured in the effective normal coefficient of restitution. In E. E. Yeah, so there's an effective E that it,
Formula doesn't seem to have that explicitly in
what formula?
L over D. Wouldn't it depend on EP?
Well, that's a good point. I mean, so it doesn't. So L over D doesn't explicitly depend upon the coefficient of restitution. However, it does depend upon the effective coefficient of restitution through the influence that the effective coefficient of restitution has in the determination of T. Okay? Yeah, so I mean, it's there, but not explicitly, directly. Okay, you guys are going to be experts by the end of.
That's the aim of these lectures.
Is that it? I thought it was to exhaust the audience until they capitulated. Okay, so where am I now? Okay. So the question is, how do we use all this? How do we use this? And so the answer is, we're going to use, we want to determine the temperature. We want to determine the temperature using the energy balance, but the simulation of Matari and Nakanishi said we didn't need the divergence term. That is, at least in the core of these inclined flows, we just need the algebraic balance between the rate at which fluctuations are being created and the way they're being destroyed. So that observation of Matari and Nakanishi then gives us a relatively simple algebraic problem to determine the temperature, for example. And we've got all the ingredients. That is, we have our constitutive relation. We have our constitutive relation relating this quantity that appears in the expression for L to the ratio of shear stress to the pressure. And remember that in the steady inclined flows, the ratio of the shear stress to the pressure is equal to the tangent of the angle of inclination. So that's a given constant, okay? So, and J, remember we had J that in the simplest theory is unity, in a more refined theory for frictionless particles is 1 plus pi over 12, but in a theory for more dissipative particles is a more complicated function of the effective coefficient of restitution. Okay, in some place along here I'll write it down so you can see it in its full glory. Okay, so the way I'm going to determine the temperature and then eventually everything else, the mean velocity, the volume fraction, is by first determining the temperature as a solution to the algebraic form of the energy equation. Well, I guess I've done something a little bit earlier there. So what I've done is I've used the energy equation and the expression for L over D in order to get an expression for the stress ratio as a function of G. Okay, and the point is where the simplest theory would have given a constant value, so the simplest theory would have given a constant value. The more sophisticated kinetic theory would have given you a slightly increasing value by virtue of the fact that now in this modified theory, we're dividing through by G to some small power, but still we're dividing through by a rather strong function of area fraction. What this is predicting for the behavior of nu, let's say between 0.5 and let's say 0.6, is something like this. Okay, so this one modification of the theory gives us the behavior of the between the angle, tangent of the angle of inclination and the volume fraction. Okay, so that's one step in the correct direction. Let's see, and
Wasn't it derived from dynamic equilibrium? Isn't it just a consequence of a free-body diagram that S over P should be independent of essentially anything except the inclination?
well, this is coming as a consequence of the constitutive relations of the kinetic theory. I mean,
No, but the first time you wrote S over P is tangent of phi.
yeah,
I thought you just do a control.
yeah, that's just a momentum balance. I mean,
Yes, so then how can momentum balance be violated now just because you have different financial?
well, let's say, so we said S over P was a constant, okay? But the kinetic theory provides us with a constitutive relation for S and a constitutive relation for P that are relatively complicated functions of the strain rate, the temperature, okay? And it's,
Constitutive relations cannot violate momentum.
no, it doesn't violate it, but they serve to determine quantities that appear in them. Okay, so the fact that the stress ratio is constant then serves to determine the volume fraction, for example, as a function of tangent of angle of inclination. That is, this equation, I mean, maybe I didn't write it in a suggestive way. So this quantity is a constant. We know all of these various things. This is a complicated function of volume fraction, but we can invert this equation and we can get volume fraction as a function of tangent of inclination from this relation. That's what we're doing.
But S over P is always.
It's a constant. You're right. It's a constant. Momentum balance said it's
It's
SO.
always tangent of it.
Yes.
You can't change that.
In the steady flow.
Yes.
Yeah, yeah. So that's what we've used. We've used that fact and these extended constitutive relations. We've taken an L. Yeah, okay. And in a similar way, all of this is just a calculation then. In a similar way, we can determine, so given this determination of pressure, the pressure is just varying hydrostatically in the direction normal to the incline. A calculation then gives us the profile of temperature and, as a function of the normal coordinate and the thickness of the flow. And similarly, we go back to, we integrate this equation, having determined what the temperature is. And we obtain velocity profiles through the depth of the flow. Here, for some reason, I've given the velocity profile as a function of pressure. And I think, in fact, that's the way we determined it, was to parameterize the problem instead of in terms of P rather than Y. Okay, in any case, we've got the velocity distribution as a function of Y through the variation of P.
What is the dot over equal to sign? P equal to 2 rho G. Say.
Oh, this means, let's say, I say approximately. Why do I say approximately? I mean, I may have said approximately because the dilute contribution is ignored, but I'm not sure. Okay. Okay, so here are predictions then. The prediction is through the volume fraction. So here we have various angles of inclination. The volume fraction through the depth of the flow is uniform, strictly uniform, if we're just focusing attention on the core, okay? And not only is it uniform, but the uniform values have the appropriate ordering with respect to angle of inclination. The most inclined flow has the least volume fraction, and the least inclined flow has the greatest value of the volume fraction. So we make that change, and we get then the appropriate nature of the volume fraction and the ordering of the volume fraction. Okay? That's good. What else? And we generate reasonable velocity profiles. So here are velocity profiles. We can compare them with the simulation. I say they're in relatively good agreement with the simulation. And here are profiles of the granular temperature, or in fact the fluctuation velocity, made dimensionless in an appropriate way. And they do involve larger values near the bed and decreasing as you go to the free surface. Okay, so we declare a victory. Okay, so now what to do? Let's see, what time is it? I'll talk a little bit. Okay, so that's fine. So that's numerical simulations. We use numerical simulations to inform the modeling. We did some modeling, phenomenological now, introduced an additional length scale, and we seem to have obtained a theory that has the ability to predict what's seen. Yes?
So what was wrong in kinetic theory that it was predicting higher
So the determination of the temperature was wrong. By putting in this quantity L, we were essentially lowering the temperature systematically, kind of an effective temperature systematically, and that had, so L really is more or less proportional to the shear rate. So it's putting another factor into the energy equation. So it's a significant modification of the rate of dissipation of energy. That's what we're doing. We're lowering the rate of dissipation of energy. And that, in a way, that has a functional character too, and lowering it with this functional characteristic. So coming with this du prime over t to the 1/2, that seems to capture the physics of how the assumption of molecular chaos is failing. Okay, so that's the ingredient that makes the theory predictive in the good sense, I think. And it's remarkable, really, that you can do it in a relatively easy way, I would say. I haven't done anything that's so mysterious, I feel, but maybe I'm just accustomed to it now. Okay, so that was numerical simulations. I don't know how much farther I'm going to go. So I'll just say what I'm going to do, maybe, and then I'll save it for the next time. So now what I'd like to do, I went from numerical simulations. Now I'd like to look at physical experiments and see now how we use this extended kinetic theory, that's what I'll refer to it as, in order to attempt to reproduce the results of physical experiments. And I'm going to look at a physical experiment that was done in France that had to do with flow of particles released from a bin down the surface of a heap of like particles for various values of the thickness of the cell. So they were generating flows that over a certain range were steady and fully developed, and they were measuring how the volume flux per unit width of the flow varied with tangent of angle of inclination. And for various values of the width of the cell. Okay, so I'm going to try to go after that data with the theory that we've just developed. And of course, I'm going to do very well. And then I want to involve, I want to discuss another experiment, of a more or less similar type, involving a rotating drum, roughly half filled with particles. And these drums were of various diameters, various thicknesses. They were rotating at various speeds, and they're similar. Similar results having to do with the depth of the flow, or the height of the flow, versus a certain scaled volume flow rate. Okay, but I think I'm going to stop there. That is, next time I'll do these physical experiments, and what else? And I think I'll have time. I'll go from physical experiments to an attempt to characterize natural flows, debris flows. Okay, so we're trying to apply it to less and less artificial simulations, and you can be the judge of how successful we are at the end. Okay, thank you.